Welcome, honors chemistry student. We are now undergoing a continued study of gases with Unit 11. In essence, these are a summary of our topics, and in your student note packet, there's also a summary and an expansion upon these topics. To be transparent, this chapter is a problem-solving chapter. We will learn 3 different types of problem solving. The first, molar volume. What is it? When can we use it? And then how do we use it? The ideal gas law and gas stoichiometry. So to begin, our first lesson will involve molar volume. But to give us a little bit of background, so in your unit packet, I do have a little bit of guidance for our first bit of note-taking. Remember, gases were neglected to really be studied and strove to be understood because the majority are odorless, colorless, tasteless. So our first understandings came from investigating the relationships that we pursued last unit, the relationships of temperature, pressure, volume of gases. Then the turn came to understand gases in reactions, trying to really find the relationship between mass and volume. Volumes were, what we were measuring, but how do we assess the mass of a gas, and how do we really connect mass to volume? So the first individual that gained some evidence, Gay-Lussac. Remember, in these early days, we were, the atomic theory had just been published, and you're really working on convincing the world that atoms existed. We had very few accurate, correct formulas. And so they had an idea what hydrogen was, but an incorrect formula, idea of oxygen, idea of water. Actually, they thought water was an element for a long time. And so we just have to remember they were a bit limited. So Gay-Lussac reacted volume quantities, and we didn't have the metric system yet. So we'll just call it volume. So maybe that was a certain cup or a bowl that was just used consistently. So imagine that Gay-Lussac would analyze how much hydrogen needed to react with how much oxygen so that there wasn't a limiting factor. We didn't have any excess. All reactant reacted. So we found that when adding hydrogen and oxygen, it required a ratio of 2 volumes of hydrogen to every 1 volume of oxygen. The thought is, well, maybe reaction of gases is conserved. Volume is conserved just like mass. Well, when he would carefully measure, he found, in this case, it's not conserved. 2 and 1 yielded 2 volumes of water. So not 2 and 1 yield 3. And then looking at just another possible reaction, when he would react 1 volume of hydrogen, it would react completely with 1 volume of chlorine, and we get 2 volumes of hydrochloric acid. So it seemed like it was conserved here, but not here. So the conclusion he could make, which was a sound conclusion, not that volume is conserved like mass is in a chemical reaction. However, when gases react or combine, as far as the reactions he was looking at, they react in small whole number volume ratios. So today we would say 2 milliliters of hydrogen react with 1 milliliter of oxygen to yield 2 milliliters of water. Small whole number ratios. This will come in very handy when we do gas stoichiometry. So remember this, volume is not conserved in a chemical reaction. It seems like, it's a bummer, but still a finding. Well, Avogadro, building on this, was actually responsible for what we credit to be Avogadro's principle, So because of this work, we name Avogadro's number, but it's because of this work. And what he found was this. If you have two gases at the same kinetic energy, they are delivering the same overall collisions, number and frequency overall, and exist in the same amount of space. If these three conditions are identical for two gases, then they must have the same amount, the same number of moles, which will translate into the same amount of particles. Now, if they're different gases, they will not have the same mass, but the same number. So imagine if we would have two vessels that had the same temperature, the same volume, the same pressure. Well, if we knew the amount, 10 gas 1 particles, well, then we would know that this gas also had 10. So if they have the same amount, the same temperature and volume, then we know they have to have the same pressure. If they have the same pressure and temperature and amount, they have to have the same volume. So we can make this relationship. It does not matter the identity of the gas. It doesn't matter if it's hydrogen and laughing gas. It doesn't matter if it's helium and oxygen. The identity of the gas does not matter. There's so much empty space that if it's hydrogen, diatomic, or a more complex, larger molecule, doesn't matter. There's so much empty space that the actual identity of the particle only would matter in the case of mass. Okay, so then, getting ourselves to molar volume, which builds on the previous things that we talked about. So we have used, molar volume. We have used a lot molar masses in our calculation. So to remind us, molar mass, if it was just mass, the unit would be gram. But molar mass, if I asked for the molar mass of water, I know you would go to the periodic table, add up 2 hydrogen average atomic masses and 1 oxygen, and we would get 18.02 gram per mole. Molar mass, the mass of 1 mole of a substance. We use these, of course, in conversions. We can get molar mass of anything that we have a mole of, a compound. Now, usually we do call it average atomic mass, right? So 32.07 would be the average atomic mass. But again, we could call it molar mass as a mass of 1 mole. But we usually use the term molar mass or formula mass with compounds, average atomic mass with individual elements. All right. Mass is constant. It does not change when temperature changes, pressure changes. Molar volume. So if molar mass, gram per mole, what would molar volume be? A unit of volume per mole. Now, this could be any unit of volume, but practically for this chapter will most often be in this liter per mole. So what kind of things do we measure in liters? Well, usually fluids, so liquids and gases. So molar volume would be the volume of 1 mole of a substance. Specifically, though, when we use the term molar volume, we are talking about 1 mole of any gas. Remember, the identity does not matter. So this could be nitrogen or oxygen or carbon dioxide or water vapor. 1 mole of any gas. However, the temperature and the pressure do matter. So if we had 1 mole of gas at 0 Celsius, 1 atm, it would occupy a volume of 22.414 liter. That is the volume of an average beach ball. So when we talk about molar volume, or we are solving problems applying molar volume, we are talking about liters per mole of a gas, any gas. The value is 22.414. We want those 5 sig figs. It is experimentally determined, so it can limit our sig figs, but this is only true at STP. All right. So I don't know about you, but I sure see that that's a conversion factor. So we can utilize this relationship to get us from liters to moles or moles to liters, as long as we're at STP conditions. So let's dig in to some sample problems. Okay, so if we take a look at this first, the first thing that I see loud and clear, we are at STP. You'll either be at STP and told such, or not at STP and then told those conditions. See, in both of these examples, yay, we're at STP. And what that tells you is you have permission whenever you need it, if you need it, to use 22.414 liter per mole to relate volume and moles of a gas. So we start with our given, and we are asked here to find volume in liters. You can always put that over 1 if you want. We're at STP. It doesn't mean we will use this, but we have full access to. Well, let's see. I want liters. I need to cancel moles. Can I relate moles and liters? Absolutely. And when you do this math, this could limit us to 5 sig figs, but we're limited to 3. So as you see, our answer, 1.52 liters of oxygen. Next, we're at STP. Yay! So we can use this. We have full access to it. So we're starting with 98 milliliters of sulfur dioxide and ask for grams. Well, molar volume is liter per mole. If these problems are under the heading of molar volume, or the problem says to apply molar volume in your problem solving, we know this is going to be somewhere in our problem solving. So since that relates liters and moles, and I'm given milliliters, my first thought is to get to liters. And it would be of the SO2. Doesn't limit sig figs because of the relationship that is defined. Then I can use molar volume to get moles, and then moles to get me to grams, because I know my formula, and we have 64.07, and we got, yay, 0.280 grams of SO2. All right, so moving right along. We did not last chapter actually calculate and work numerically with density of gases. We know they have very low densities. In fact, we commonly report them in units of gram per liter versus liquids and solids in gram per milliliter. We need a much bigger volume to have a workable mass. That's just a reasonable number to be writing. Okay, so let's just say we want to do example 4. We're asked to find density. We know density is mass per unit volume, which is going to be, with gases, usually gram per liter. At STP, yay. So we can utilize 22.414 liter per mole for any gas whenever we need it. Well, if we take a look, oh, We don't have a number and unit given for this problem. Ah, but I know my formula. I know my formula. And if I know my formula, I can easily get its formula mass or molar mass. So add up 1 sulfur and 2 oxygen, 64.07 grams of SO2 per 1 mole of SO2. Well, I don't want gram per mole. I want gram per liter. So I need to cancel the mole, but leave the gram. Okay. So I'll put mole of SO2 in the numerator to cancel. I can use molar volume to then cancel moles. This is a true relationship, and I get gram per liter as my answer. And we should get that 2.86 gram per liter SO2 as our answer. All right, so those examples show us how to apply molar volume at STP conditions.